Hello guys, welcome back to Infinite Insight Geometry, lesson 3.6. Congruent parts of congruent triangles are congruent, otherwise labeled as CPCTC. Alright, let's begin. So, how can we use congruent triangles in proofs? Well, we know that corresponding parts of congruent triangles are congruent already. That's what corresponding parts are. But how can we use this congruency theorem in proofs? Proving two triangles congruent makes all their congruent parts equal as well. Usually most advanced proofs involving quadrilaterals and circles, or trapezoids, or squares, or rectangles, they all start with proving two triangles congruent, and then using those corresponding parts to prove other parts congruent. Let's take an example. If angle EBC and angle ECB are congruent, and angle EAD and angle EDA are congruent, prove that AC is equal to BD. I'll give you a moment. Now, here is the two-column proof. As you can see, you have your statements and your reasons. And the other thing to note about this figure is that since it has 4 points and 4 sides and 4 angles, it is a quadrilateral. What we'll come to know as an isosceles trapezoid, but we'll learn that when we get to quadrilaterals later in another unit. But it goes to show that congruent triangles are very important when proving quadrilaterals or circles or any sort of proof that has a hidden triangle inside. So let's try and find some of those triangles. If you have angle EBC and angle ECB are congruent, and angle EAD and angle EDA are congruent by its given, what can you say about those triangles? Well, you might want to start first by naming these triangles. Triangle EAD, as you can see over there, is isosceles because it is a definition of an isosceles triangle. It has two angles that are congruent. That's the definition of an isosceles triangle. And we can also say the same thing with triangle EBC. It's also isosceles. If you can see the triangle EBC, you can see that angle C and angle B are congruent, meaning that EBC is an isosceles triangle. Now, the converse of the isosceles angles theorem. Now, I didn't show this before, but most of the converses, if you want to prove them, of the theorems that we've learned so far, are true. The converses of the theorems that we proved so far are usually true. And that so is the case for the isosceles angles theorem. The converse of the isosceles angles theorem is true. And so we can use them in proofs. If you want, you can go back to the triangle basics where I discussed isosceles angles and triangles, and you can figure it out for yourself. Try to make a two-column proof of that. But all you need to know for this lesson is that the converse is true, and therefore we can prove that AE is equal to DE and BE is congruent to CE. Now, what does this do? AE is congruent to DE and BE is congruent to CE. If you see what this actually means for these triangles, you can see that AE and CE is part of a triangle of A, E, and C. If you connected the points A, E, and C together, they make a triangle. And same is D, E, and B. Now, if we can prove these two triangles congruent and correspond AC to BD, then by parts of congruent triangles are congruent, we can prove that AC is congruent to BD. So, how would we do that? Well, we have two sides, but if you only have two sides, you need to either, one, prove the other side congruent, prove the third side congruent, and solve it using SSS congruency, or you can also prove the included angle congruent to each other. Now, how would we do this? We prove that AE is equal to DE and EC is equal to EB. What's next? Well, the next step is to prove that angle AEC is congruent to angle DEB. How would we do that? Now, look at AB and CD. They are intersecting lines intersecting at E. That's the definition of intersecting lines. That means that AEC and angle DEB are vertical angles. That's the definition of vertical angles. And if you can see, when two lines intersect, they make vertical angles, as we've discussed before. By the vertical angles theorem, angle AEC is congruent to angle DEB, and now we have everything to prove these two triangles congruent. Triangle AEC is congruent to triangle DEB because AE is congruent to DE, angle AEC is congruent to angle DEB, and EC is congruent to EB. So we can prove triangle AEC is congruent to triangle DEB, congruent by the SAS congruency, side, angle, side, because there are two sides and their included angle. Meaning, if we look at all of the corresponding parts, we can see that AC is in fact a corresponding part of BD, meaning corresponding parts of congruent triangles are congruent. AC is congruent to BD, and the lengths are congruent, are equal. So AC is equal to BD. Now, this was a pretty long proof. We will be going over many other proofs like this in the next few lessons. But just know that usually in these types of proofs, what's needed is imagination. You need to know what to be able to do, know the flow of the proof, know how to move from one step to the next logically and consistently, because there will be lots of proofs going forward. And most of them will be using congruent triangles to prove two things congruent, and that's usually very much needed in quadrilaterals, circles, other polygons, even three-dimensional shapes. That's why triangles are so important. That's why they're usually put first in most geometry courses, and of course in Infinite Insight Geometry. This is the foundation that will help you learn more about other proofs. And that'll be all for today's lesson. If you liked the video, please like and subscribe. I have my email down below if you have any questions. I'll see you all next time.